Hello, everyone, and welcome to Virtual Planetarium from the Museum of Science. My name is Emily. My pronouns are she and her, and I will be your moderator during this program. And that basically means that I am the one watching the Q&A box right here in the Zoom webinar. So if you have a question or a comment at any time throughout the program, drop it into that Q&A box just by clicking on the Q&A button on your screen. We're also offering closed captions during this program, so if you would like to see subtitles, please click on the CC button on your screen and select Show Subtitles. So with that, we're going to bring on our main educators and we'll get started.
Thanks, Emily. Hi, everyone. My name is Katie. My pronouns are she and her, and today I will be your educator as we explore some of the most mysterious topics in space, but I can't do it alone.
Hello, everybody. My name is Talia. I also use she, her pronouns, and I'm going to be handling the visuals today.
And visuals will be kind of weird because today we are talking about dark matter and dark energy. A lot of the times these two terms are conflated and we hear them together quite a bit, but they are two different things, and they are names for things in the universe that we really know nothing about. So the term given to the thing responsible for accelerating the expansion of the universe is called dark energy. We're going to talk about that a little bit later. And then dark matter is the term given to all of the missing material in the universe. So we don't know what dark matter would actually be made of. We've never detected it. But we know that it has to be there because of all of these interesting gravitational effects that we see happening in the universe. So we're going to start with dark matter and transition over to dark energy later in the program. So dark matter, it does not interact with light. So the only way that we can detect it is by looking at its gravity. Dark matter itself is thought to compose 85% of all matter in the universe. Now, this particular pie chart that we're looking at is a little bit different. So that yellow slice right there is ordinary matter, which is also called baryonic matter. So things that you can see, like stars, nebulas, galaxies, planets, all of the stuff that we generally think of when we're thinking of space, even things like black holes, are considered ordinary matter. They interact with light. So even if our eyes can't see it, but if it interacts with light in some way, meaning if it emits light, absorbs light, reflects light, anything like that, that is baryonic or ordinary matter, and it's about 5% of all matter in the universe. Dark matter makes up the rest of physical matter. The rest is just energy in the whole universe, but we got a significant chunk dedicated to dark matter, and then we also have dark energy. So this pie graph is telling us how much matter and energy there is in the entire universe, because matter and energy are very, very similar. In a lot of ways, you can almost think of stuff or matter as being energy slowed down or confined energy. Think of Einstein's equation, E equals mc squared. Mass and energy are very, very closely related. So we can kind of just take all of the mass and energy in the universe and make this chart. So only 5% is the stuff that we can see. All right, so how do we know that dark matter exists if we don't know what it is? We can't see it. It's very mysterious. And the first thing that we can look at is our own galaxy. So last week, Talia was talking about our Milky Way galaxy, and this is a model of it. Our sun in our solar system is located in one of the spiral arms, about 2/3 of the way from the center of the galaxy. There are about 300 billion stars in our Milky Way. It's about 100,000 light years across, and we're just one tiny little speck in this entire model here. At the center, we can see this big bulge of light. That's where lots and lots of stars are all orbiting around the central supermassive black hole at the center of the galaxy. And from last week, this supermassive black hole that Talia was talking about is keeping a lot of our galaxy together. A lot of the stars are orbiting around the supermassive black hole, but that's not the only thing that is keeping our galaxy together. Astronomers believe that our galaxy has a lot of dark matter in it as well. And the reason they think this is because of the speed of stars in the Milky Way. So at the center there, stars are orbiting very quickly, and you would expect that the farther out you go, the slower stars would orbit, kind of like in our solar system. The sun is the most massive object, and objects that are closer to the sun orbit faster than objects that are farther away. So like Mercury, the planet Mercury, the closest one to the sun, orbits a lot faster than Neptune, which is the farthest planet from the sun. This is how Kepler's laws of orbital motion work. But in our galaxy, that's not what's observed. So in this little graph here, we have that blue dotted line, A. This is what astronomers predict the motion of stars in our galaxy to look like. So on the left there, you have velocity. And then on the x-axis, we have the distance from the center of the galaxy. So on the left-hand side, those are stars that are very close to the center, and we can see that their velocities are fast. And then they're predicted as you get farther and farther away that the stars would start to slow down. But line B is what is actually observed, is that the stars don't get slower. They actually all, on average, orbit at a fairly constant speed. And the only way that would be possible is if there was more material in our galaxy than we account for. So all the mass that we can see, it's not enough for this motion of stars. So that is where dark matter comes in. If we include dark matter in our galaxy, then we are able to match our observations to this line, this distance times velocity line that we have here. On the left, that's what objects in a galaxy without dark matter would be moving like. And then on the right, we have the galaxy with dark matter, which is what we actually observe. And obviously this is very exaggerated. Everything is moving a lot faster. All right, so to give you kind of an analogy for this before I'll pause for some questions, you can kind of think of dark matter like if you were looking at a trampoline and there was a baseball sitting in the middle of the trampoline. The baseball represents a galaxy, and the trampoline itself represents the fabric of space-time. And due to the effects of gravity, that galaxy or that baseball right at the middle is going to warp the trampoline around it. It's going to warp the space-time around it. And so you would see that as a small little dip in the trampoline. Now, imagine if you were looking at a baseball on a trampoline, and instead of a small dip, you experienced the dip. You saw the dip that was going all the way straight down to the ground. That would probably look pretty confusing because a baseball is not very massive and it's not very heavy. So we're seeing the effects of something much more massive, but we're only observing part of that mass. So you can think of the dark matter as all the stuff that you can't see that's causing the bigger dip with the baseball. And that's kind of like our galaxies and the fabric of space-time. All right, I'm going to pause and see if there are questions because this stuff is really weird.
Cool, thank you, Katie. I do have one so far, and it came in pretty early, so I apologize if you already answered it. But someone is wondering, does dark matter include black holes?
So it does not include black holes because black holes we can measure, we can see the effects of black holes, they interact with radiation. So even though that if light gets too close to a black hole, it can't escape, so that's why they're black. it's still interacting with light, and we can see light orbiting around black holes, material orbiting around black holes. It's interacting with the material that we're used to seeing. And they also form from material that was in stars. So that is all actual baryonic ordinary matter, even in black holes. Dark matter is completely undetectable to us right now, doesn't interact with light. The only thing that we can really see is its gravitational effects, and that's it.
Okay, thank you. So far, that's the only one about dark matter and dark energy. So I'd say move on, and then we can do a few more later on.
That sounds good. All right, so those galaxy rotation curves, that is our number one piece of evidence for dark matter existing in the universe, but there are others. We can also look at galaxy clusters. So lots of galaxies that are gravitationally bound to each other. Galaxy clusters can be made of anywhere from hundreds to thousands of galaxies. And the more material that's present in a galaxy cluster, the faster those galaxies are going to move. So what you're looking at right now is just a whole bunch of galaxies. These are actual images of clusters of galaxies really far away and deep in our universe. And so the more material that makes up these clusters, the faster they move. And so astronomers can measure the speed of these galaxies. They can also measure how much stuff is making up these galaxy clusters just based off of the light that it gives off. And if we compare the amount of matter that's seen to the speed, it turns out that they're moving much, much, much faster than they should be with the amount of matter that we're seeing. So if we include dark matter into the mix, we get a more consistent answer. We can see that they are moving at the proper speed once you take into account both the regular visible matter and dark matter. Another way that galaxy clusters can be used to help us detect not detect dark matter, but provide evidence for dark matter is by something called gravitational lensing. So this picture that you're looking at, if we could go, yeah, perfect. So this is a galaxy cluster that you're looking at called Able, and I don't remember the number after it, but it's made up of hundreds of galaxies, and so it has a very strong gravitational force associated with it. And so it can bend light. So you can imagine a really massive galaxy or a cluster of galaxies that is in the way of another galaxy that's behind it. So that galaxy that's behind our foreground galaxy, any light that's coming from it is actually going to get bent around this foreground object and give us these kind of weird bent images of the galaxies behind it. So Talia is pointing out these particular arcs of light that are from objects behind this cluster. So we can see evidence of dark matter here because the geometry of the bending can be mapped to the amount of mass that a cluster has. And taking into account dark matter, we see this particular type of lensing. If we don't take into account dark matter, it wouldn't look exactly like this. So this is yet another way that we can detect, or rather prove that there's got to be something else. There's got to be another piece to the puzzle here. And the next slide, we can see exactly what I was probably really poorly explaining. So we've got a distant galaxy cluster, and the light from it is coming toward us. And it's being lensed by a very massive region that has a strong gravitational pull in between us and our cluster. And so in this case, this is if our lens is all dark matter but a lot of the times it's a galaxy or a cluster of galaxies that's having this effect. But we can still see that lensing happening, even if it's just a pocket of dark matter out in intergalactic space. All right, so that's how galaxy clusters can help detect dark matter. And there's one more thing before we talk about dark energy, and that is the signature of the Big Bang. So this is called the cosmic microwave background radiation. So this picture is the radiation that was actually left over from the Big Bang, the start of our universe. And the different colors that you see are tiny fluctuations in temperature. And I'm talking very, very, very tiny. This radiation is all around us. It's just kind of like this background noise in the universe. It's prevalent all over the place. And even when you turn your TV screen on and you get all the static, 1% of that static is actually due to the cosmic microwave background radiation. Now, these little temperature fluctuations in particular, their sizes can be measured to tell us more about the geometry of our universe. And this whole concept is pretty complicated and it blows my mind quite a bit. But being able to tell the size of these temperature fluctuations tells us that we live in a flat universe. And this flat universe means that we have a certain amount of mass and energy necessary in the whole universe in order for basically this picture to look the way it does. It would only work this way if we lived in a flat universe. And so through more steps, we also get evidence for dark matter having to exist in this way as well. The cosmic microwave background wouldn't look like this if it wasn't for something additional like dark matter and dark energy, actually. So this is where there's kind of a connection made between dark matter and dark energy. But before we start talking about that, have there any other questions come in?
Yeah, someone just asked, what is antimatter and how would you classify it?
Yeah, antimatter is matter that is opposite in charge. So like if you think of a proton or an electron, the opposite versions of them. So a proton is positive, or an electron is negative, and so the positive version would be called a positron. So that's considered antimatter, but it is different from dark matter. Dark matter is not believed to be the same thing as antimatter, but I don't know too much about it.
Okay. Does the radiation coming from the cosmic microwave background last forever? Or is it going to last forever?
Yeah, so eventually it is getting gradually shifted. So because the universe is expanding, and it's getting faster, the expansion is getting faster and faster, this background radiation is being stretched out. So its wavelengths are getting longer and longer. And so that's why it's called microwave radiation, because it's kind of moving toward the longer end of the entire electromagnetic spectrum. And eventually the wavelengths will just keep getting longer and longer, maybe more dispersed, but yeah, it will be there forever really until, oh gosh, until the whole universe is done. I don't know when that'll happen, but.
Let's do one more for now. Someone is wondering what exactly you mean by a flat universe. Do you mean like a plate that is much wider than it is thin?
Yeah, so I think that would be a reasonable analogy. It is kind of hard to think about, right? Because we talk about gravity warping space-time and that space-time is curved, but these things are on more like local scales, right? So when you look at the universe as a whole, it is being flattened because of expansion. And there's, again, it's kind of hard to imagine because we're living in a 3 to 4 dimensional universe, and it's hard to imagine anything like that being flat. Talia, do you mind if we go to the next slide and maybe, I don't know if this will work. The next, I think the one right after this one. This one, yes, geometry of the universe. This is a very simplistic version. But as the universe is expanding and accelerating, this is kind of stretching the space in between all of the material in the universe. And so as a whole, it would be considered very flat. But it's really hard to imagine, and I haven't quite wrapped my head around it yet either.
Does that also mean that it's getting flatter?
Yes.
Okay, cool. I think that helps a lot, Katie. We do have a couple more questions that came in, but maybe we can squeeze them in at the very end.
Sure. All right, so dark energy, and I don't have too much on this one, but dark energy is the material that is thought to be causing the universe to accelerate as it expands. So in this animation here, we have just kind of a quick example of the universe expanding after the Big Bang. And as it gets farther and farther out, it's actually getting faster. It's expanding faster. So that was interesting because astronomers figured that due to the forces of gravity, that eventually it would reach a maximum and maybe start slowing down after, because gravity would cause everything to be attracted and it would no longer be able to expand. But this is not what we see. So there has to be something that is driving the expansion and acceleration of this expansion, and that's what we call dark energy. Now, you can kind of think of the expansion of the universe like you were on the surface of a balloon. Like if you take a balloon, you draw dots all over the surface and then you blow it up. The dots are not actually moving away from each other, but the space in between them is. And that's what's happening in our universe. So if we look at galaxies that are really, really, really far away, we can see that they are accelerating away from us faster than the speed of light. And now you might be thinking this is breaking all the rules of physics, but not exactly, because it's not the galaxies themselves that are moving through space faster than the speed of light. It's the space itself that is expanding and causing that galaxy to move farther away, if that makes sense. So like on our balloon, the dots, they are not moving apart, but the space in between is. And so objects or galaxies that are closer to us are moving away at a slower rate than galaxies that are much farther away from us. So that's the universe expansion. Now, evidence that we have for dark energy comes from it's called the cosmological redshift. So if you've ever heard of Doppler shift, or if you've even just heard an ambulance go by and you kind of hear the change in sound, that's an example of the Doppler shift, which means that when the ambulance is approaching, the sound waves are getting squished together. So they sound a little bit different than they do when the ambulance is moving away, because at that point, the sound waves are getting stretched out. So you're hearing two different pitches there. It's the same thing with light. If an object is moving away, the light from that object gets stretched out a bit. And so the whole spectrum or the light signature of that object shifts to the longer wavelengths. It's the same thing with distant galaxies. We see their spectrum shifted toward the redder end, or the longer wavelength part of the spectrum. And it's not because that object is moving through space away, it's because space itself is causing that object to be farther and farther away. So this is called cosmological redshift. And then we also have to come back to this flat universe with with this geometry, there has to be a certain amount of material and energy in our universe for it to be flat. We know that the universe is flat because of the cosmic microwave background radiation and these little temperature fluctuations. Through some math and through some geometry, the size of these fluctuations, like those blue spots that you're looking at right there, they are only the exact same size that they are because of this flat geometry. So we know that there's got to be some extra energy, extra material in the universe that we are not seeing, and that's not interacting with light. And then for our last slide, which is going to be super exciting, this telescope, it's called the Nancy Grace Roman Telescope, is going to investigate a lot more about things like the expansion of the universe and dark energy, because if it turns out that there is no dark energy, then it means that everything we know about gravity is wrong. So hopefully we'll find out a lot more about that. This will be a mission launched in the next decade. All right, any last minute questions?
Yeah, we have even a few more that just came in, but I think the last one that we have time for is just one quick clarifying question. Does dark matter change the size of a galaxy, or does it work on a bigger scale?
Yeah, so the Milky Way, for example, actually has a dark matter halo around it, which we can't see, but astronomers can map where they think dark matter is based off of the motion of stars in our galaxy. So this is an animation of where astronomers believe the dark matter is. So you can see it's actually exceeding our galaxy by quite a bit. And our neighboring galaxy, Andromeda, is about 2.5 million light years away. Andromeda and the Milky Way are actually gravitationally bound and are going to collide in about 4 billion years. They haven't collided yet, but their dark matter halos are far enough away that those have already started to collide, which is kind of weird.
Awesome. Okay, well, thank you so much, Katie. Let's see, I think we can all come back on screen. Do you two want to say goodbye to everyone before we wrap this up?
Sure. Bye, everyone. Thanks for joining.
Bye, everyone. And don't worry if your brain hurts a little bit. That is the correct response to thinking about dark matter and dark energy. It's really weird stuff.
That is absolutely true. Thank you all so much for joining us today. I'm sorry that we couldn't get to all the questions, but they were all amazing, the ones that I saw. So if you enjoyed today's program, we do this every Tuesday until at least October, so you can join in next Tuesday and the Tuesday after that. We also have more virtual offerings at our website, mos.org/mos@home. And then if you're interested in supporting the museum, you can visit engage.mos.org/welcome. So with that, we will see you next week and have a great day.